Let's clue up the last section of this chapter now by talking about Gauss's law and some of the properties we already discussed about conductors. So those specific properties we discussed is in a conductor, in electrostatic equilibrium, first thing we know is that the electric field inside the conductor is equal to 0. And we know that all of the excess charge or charges, all of the excess charge is on the surface. Now here's something you might have picked up on when we discussed this earlier. I said on the surface or on the surfaces. Here's where we start talking about that again. So let's say we have a conductor, that's this odd-shaped gray blob. Inside the conductor we have a cavity. So let's start by saying our conductor is neutral. So let's start with a neutral conductor. What it means to have a neutral conductor is that there are equal amounts of positive and negative charges, and those are more or less uniformly distributed over the whole conductor. So neutral means same number of positive and negative charges. So we start with a neutral conductor, and then what we do is let's put a positive point charge in the cavity. So there's plus Q. I'll draw it small because it's a point charge. Now let's ask what happens because of that positive point charge plus Q. Well, it's positive. In a conductor, we know that charges are free to move around. So that means we're going to get negative charges attracted to that positive. Negative charge is going to get drawn to the inner surface. Oops, I wrote on Pinto's face. That's called an induced charge. Okay, so we get negative charges drawn to the inner surface. What happens to the positive charges? Well, they get pushed away to the outer surface. So positive charge induced on outer surface. So now what happens is, because we put a point charge in the middle, it causes the charges on the conductor to move around. We get some negative charge on the inner surface, we get some positive charge on the outer surface. So this condition is met, the charge is on the surface or surfaces, and it's also true that the electric field is going to be 0. Why don't we do an example and let's think about how that works. For this example now, we have a point charge Q, it's implied to be positive, in the cavity of an uncharged conducting shell. So this is like a thick-walled shell, like a balloon with a really thick wall or a bowling ball. And we're putting a positive point charge in the middle. Maybe imagine a marble in the middle of a bowling ball. So let's label our point charge plus Q. All of this white space here, this is just empty space. There's nothing here, it's empty. And the gray stuff is the conductor. And we say that the conductor is uncharged. So let's just write down that Q of the conductor is equal to 0. So there's our picture. Everything is all nice and labeled. We already talked about how charges are going to move around. So there's a positive charge here. We know that the negatives in the conductor will be allowed to move. So they're going to move to the inner surface. They're attracted to this charge. The positive charges are repelled by our positive point charge. So they're going to move to the outer surface. But how much charge? Let's try and figure that out. You might already have an idea, and let's see if your instinct is correct. So we'll begin by writing down Gauss's law, which says that the net electric flux through any closed surface is the integral of the electric field over that closed surface, and that's equal to the charge enclosed by the surface divided by epsilon naught. And the next step is let's deal with our Gaussian surface. We would like for it to be symmetric with our charge. Since our conductor is spherical, let's make sure our Gaussian surface is a sphere. With radius r. We also want it to be useful. So this one could be a little bit tricky. How do we make it useful? Well, let's ask, do we know anything? This is a conductor. So one thing we know is that the electric field inside the conductor in the gray space, that electric field is 0. That's something we know. That feels useful. So let's have the radius of the sphere. Radius is inside the conductor. And we're choosing that because we know that the electric field there is 0. And now we'll draw our Gaussian surface. Again, this should be a perfect sphere, but I do not have a perfect hand. Okay, so now let's apply what we know to our Gauss's law. The integral of E dot dA is equal to Q enclosed, the net amount of charge enclosed by our Gaussian surface. So that's the net amount of charge inside the blue dotted line that I drew. We know that our electric field is 0. So the conclusion is that the net amount of charge enclosed by our Gaussian surface must be 0. Okay, that's kind of a big result. Now, let's try and reconcile that. The net amount of charge has to be 0. We know that there's a positive point charge here. And we also know something else. We know that this positive point charge attracted some negative charges. So I'm going to draw those in my picture. So it attracted negative charge to the inner surface. So we know that the inner surface has an induced charge. Let's call that induced charge Qi. Qi. So Qi equals charge induced on inner surface. Okay, so the net amount of charge inside the dotted line is equal to 0, and the net amount of charge is whatever charge is on this inner surface plus the point charge. Okay, so let's do that. So Q enclosed equals the point charge plus Q plus the charge on the inner surface, and Q enclosed equals 0. So that tells us that our point charge plus Q plus the charge on the inner surface equals 0. So the charge on the inner surface is equal to minus Q. It's opposite in sign and equal in magnitude to our point charge. And that makes sense. So for however much positive charge we have here, that's how much negative charge is going to be attracted to this surface. Okay, so there's one result. What about the charge on the outer surface of the shell? So remember, the negatives got attracted to the inside, the positives get attracted to the outside. Let's call QO the charge induced on the outer surface. So QO equals charge induced on outer surface. We know that the net charge on the shell equals 0. So net charge on the shell, Q of the conductor, equals 0. And we know that because it was given as uncharged. And the net charge on the conductor is equal to whatever charge is on the inner surface plus whatever charge is on the outer surface. So if you add up this charge to this charge, you get the total charge. Let's put those two statements together. 0 equals Qi plus QO. So QO equals negative of Qi equals negative of negative Q equals plus Q. Okay, so that makes sense. If we have negative Q on the inner surface, but the total charge has to be positive, that better put plus Q on the outer surface. So now we've figured out the charges induced on the inner and outer surfaces of the shell. Last part, sketch the electric field. So the last part is to sketch the electric field. Let's use what we know about electric field, and that's that electric field goes out of a positive and into a negative. And we also know that electric field is zero in a conductor. So that means an electric field line can start on my positive charge plus Q, and it goes up into the negative surface. My electric field in the conductor is zero, and then my electric field will start at the outer surface and go away. So that's what the electric field looks like. That's one line. Let's draw a few lines. So it goes away from the positive into the negative, and then away from the positive. Remember that electric field strength is proportional to the amount of charge. And that matches our picture. So the amount of charge on the inner surface is equal to the size of the point charge and is equal to the size of the charge on the outer surface. So we'll have the same number of lines coming out of the point charge as go into the inner surface. And then that same number of lines goes out of the outside one because they all have the same magnitude of charge. For a homework question now, let's look at the same problem, but here we'll say that the point charge is 1 microcoulomb and the radii of the shell is 0.125 meters on the inside. Oops, that should be 0.175 meters on the outside. How much charge is induced on the inner and outer surfaces? And find the electric field at 0.1 meters, so in the cavity, 0.15 meters in the conductor, and 0.2 meters outside the conductor. That one might be a little tricky, so I think actually maybe I will make a video for that one and post it along with the class notes.